Okay guys, welcome back to another video. Today we're going to prove that let a and b be positive integers such that a divide b square divide a cube divide b to the fourth, b to the fourth divide a square, a to the 5, and a to the 5 divide b to the 6, and all the way and so on. Okay, and show that a equal to b. How can we do with this? So the first thing that I want to do is to let a and b be positive integer and try to write the general form of this divisibility. As you can see, we have a divide b square, a cube divide b to the fourth, and a to the 6 must be divide a to the 5 must divide b to the 6. So we have to start with a being odd number. So we gotta have to assume that a to the 2n minus 1 divide b to the 2n. Okay, and when you want to divide the exponent of a, we have to start with b square divide a cube, b to the fourth divide a to the 5, right? And b to the 6 divide a to the 7. So we need to start with even number of the exponent of b. So we gotta have b to the 2n divide a to the 2n plus 1 for every positive integer n. And we try to show that a equal to b. Okay, so how can we deal with this? So we might want to use the property of divisibility here. I think you will know that when a divide b, we gotta have integer q such that b equal to a q. But I think this one is not, but I think this divisibility is not useful for this. I think we have to use properties. Okay, so I want to choose this one. Number 7 is quite promising. So we need to have a divide b, and b is not 0. Then the absolute value of divisor is less than or equal to the absolute of b. So for this one, we have to use the property. Okay, so by the property of divisibility. So what do we have here? We gotta have 2 or a to the, from this one right here, a is the divisor, b is 2 to the n. And it's obvious that a to the 2n minus 1 and b to the 2n are positive. So a to the 2n minus 1 is going to be absolute value of a to the 2n minus 1. And it must be less than or equal to absolute value of b to the 2n because of this one. Okay, this divisibility. And b square, b to the 2n is b to the 2n. Okay, and for this one, we also use the property of divisibility. So we gotta have b to the 2n, which is absolute value of b to the 2n, less than or equal to absolute value of 2n plus 1, which is a to the 2n plus 1 for every positive integer n. Now, from these properties, we gotta have we will have a to the 2n minus 1 less than or equal to b to the 2n and b to the 2n less than or equal to a to the 2n plus 1. And then what do we have next for every positive integer n? So we have b squared here, b to the 2n here, and b to the 2n here. That means that we can have a to the 2n minus 1 less than or equal to b to the 2n less than or equal to 2 to the 2n plus 1 for every positive integer n. Okay, so what can we do next? We try to show that a equal to b. So what can we do? So I think we have to try to erase n. Okay, try to erase the exponent, but we cannot erase directly. I think we have to use log. So now we know that log, especially log base 10, which is the log with the base greater than 1, is increasing. We know that it is increasing. It is an increasing function for x greater than 0. And we have this inequality here. Now, what do we have next? So we can take log all the side of this inequality. So we're going to have log a to the 2n minus 1 less than or equal to log b to the 2n less than or equal to log a to the 2n plus 1. Okay? And then we write this exponent into the front of log. So we're going to have 2n minus 1 log a less than or equal to 2n log b less than or equal to 2n plus 1 log a. And we divide both inequality by log a. Wait, can log a be 1? Can log a be 1 in this case? Okay, if you divide, if a is 1, here's what happened. When log a is 1, we gotta have 0. Okay, we gotta have 0, right? So now we get that we want to divide by log a. Okay, multiply by 1 over log a. 2n minus 1 log a less than or equal to 2n. Okay, 1 over log a times 2n log b less than or equal to 1 over log a. Okay, times 2n plus 1 log a, where log a is not 0. Okay, so this log will be cancelled and this log will be cancelled. So it turns out to be 2n minus 1 less than or equal to 2n log b over log a, and less than or equal to 2n plus 1. And then divide by 1 over 2, by 2n. So we gotta have 1 over 2n times 2n minus 1 less than or equal to 1 over 2n times 2n log b over log a less than or equal to 1 over 2n times 2n plus 1. Then we're gonna have 1 minus 1 over 2n less than or equal to log b over log a less than or equal to 1 plus 1 over 2n for every positive integer n. For every positive integer n. Now, what can we do next? So, since this inequality is whole for every n, so I will try to let n approach infinity. So as n approach infinity, okay, what do we have? The limit as n approach infinity, 1 over 2n, okay? 1 over n, sorry, 1 over 2 times n is going to be 0. Hence, what do we have? We gotta have the limit as n approach infinity of 1 over 2n less than or equal to the limit as n approach infinity of log b over log a less than or equal to the limit as n approach infinity of 1 plus 1 over 2n. This one approach to 0. This one approach to 0. So we gotta have 1 minus 0 less than or equal to. So since this log b or log a does not have n, so we just have log b over log a less than or equal to 1 plus 0. That means that we're gonna have log b over log a greater than or equal to 1 and less than or equal to 1. That means that we're gonna have log b over log a equal 1. So we're gonna have log b equal log a. That means that we're gonna have a equal to b. So we have shown that a equal to b. So if you have this property, we have shown that a equal to b. And that's it for this video.